here's our old friend 2x plus 1. Now I want to know what the tangent line looks like at x equals 1. What would the tangent line look like for this function?
Well, we all agreed that it was like the same.
The same as what?
2x plus 1.
Yeah, if I ask you what is the instantaneous rate of change at x equals 1 for the line 2x plus 1, what would you tell me? What is the instantaneous rate of change? What is the value?
2.
It's 2. How do I know that? It's always 2. What about here? It's 2. Here, 2. Again, instantaneous rate of change for a line, that's what we've been dealing with. What's the average rate of change between these 2 points? It's 2. The average rate of change is the instantaneous rate of change, is the slope. It's all of this. I want to know what is the slope or instantaneous rate of change of the function x squared minus 4x at x equals 1. Well, first thing I need to do is find 2 points that are really close to each other. So for the function x squared minus 4x at x equals 1, first thing I'm going to do is solve for the y value. Because in order to get the equation later on of the tangent line, you need a point. What is the y value at the x value of 1? What is it? What is it? Negative 3. You just plug in y equals x squared minus 4x. I would recommend doing that first, always getting it out of the way. So that point is separate. Okay, I have the point. Now, I'm just going to do all these calculations, all this algebra, to solve for the slope. Okay, you see there's 2 different things. So here's my slope, and so I have the point 1. At 1, I have negative 3. And I'm going to go to a point really close, 1 plus h. And I'm going to plug that 1 plus h into the function. And when you do that, you get 1 plus h squared minus 4 times 1 plus h. There's your point. Now you have 2 points that are really close to each other. And I want to find the rate of change between them. So you're still going to do y2 minus y1 over x2 minus x1. It's the same. What I would suggest, Ellie, is always if you have a mess here, simplify all this first. And you guys do that for me now. Take this as you wrote the point, and then do all of the multiplying out, combining the like terms. Do that before you put it into your slope equation. And it'll minimize errors. So do that now. At the point A, because the problem with what we've been doing is if I say in that last example, and you go through all the work, at x equals 1 and you get the number value 2, it's like, oh shoot, you know what I meant was I wanted x equals 4. Can you redo everything? You're going to be like, seriously? I just did all the work for 1. Why are you making me do 4 now? So what this is saying is, okay, what if you want the instantaneous rate of change for some dummy variable a, where then you can afterwards plug in x equals 1 or x equals 4. Does that make sense? What a is, David? So let's go through the same process. So this is the function 2 over x. And what we're going to do is just go through the same thing. And I want to know the instantaneous rate of change for any x value I want to put in later, Joanna. Any x value later. Now I'm going to call that a. So I have the 2 over x function. Y equals 2 over x. I'm going to plug in the point a. And at a, what's the y value? 2 over a. Just plug in the a value. And then I'm going to take a point really close. I'm going to call it a plus h. And that's going to have the y value of 2 over a plus h. I want to evaluate the limit. When h gets really small, for the change in y over change in x. 2 over a plus h minus 2 over a all over a plus h minus a, which is just h. And this is why we practice this summer, because these are going to come up. We have fractions and fractions, and you need to simplify that. You need to simplify the complex fraction. What I would do first, and what I said last time, some people may have errors in that last multiplying out. You see how this says minus 2 over a, Michelle? Keep track of that negative sign. Make it plus a negative 2 over a. So you know exactly where that negative sign is. Okay, Jessica? Now, this is where you can either use the Seitz way or Remus way. Which way do you like better? Whichever way you want. I like using the Remus way just because it's the same every time. So I'm going to combine these two terms together, and then I'm going to divide by h is the same as times 1 over h. Does that make sense, Jesse? So in order to get a common denominator here, I need to multiply this thing by a over a, and this thing by a plus h over a plus h. When you do that, you get limit. Can you see this green? As h approaches 0? No? Okay. 2a over a plus h, plus a negative 2a plus a negative 2h over a plus h, all over h. Now you have a common denominator up top, so you can combine the numerators. And you get limit as h approaches 0 of 2a minus 2a's cancel out. So you're left with minus 2h over a plus h divided by h. I'm going to write it over there. Combining those numerators, the 2a and the minus 2a are going to zero out, leaving you just with a 2h in the negative 2h in the numerator, divided by a times a plus h, and all of that was divided by h. Dividing is the same as multiplying by the reciprocal. So this is the same as limit as h approaches 0 of negative 2h over a plus h times 1 over h. Two fractions multiplied together, you multiply them across. When you do that, what's going to happen? The h's are going to cancel out, leaving you with the limit as h approaches 0 of negative 2 over a times a plus h. Now can you finally plug in an h value equal to 0? You can, and what do you get? Negative 2 over a squared. What does that tell you? What does that mean? What is that? What did we just solve for? What did we spend all this time trying to solve for? Yeah, that's exactly what it is. It's the instantaneous rate of change of the function 2 over x at any x value. And we're going to call that x value a. So for example, if I want to know the instantaneous rate of change for this function at an x value of 1, what is it? Yeah, you can just plug it in then. You know what I'm saying? But then if I was like, oh shoot, you know what I meant? I totally meant 2. Sorry about that, can you redo the entire problem? You can be like, I just plugged in an a. So what would the instantaneous rate of change be at 2 then? What would it be? Does that make sense? You can just kind of like, it's harder up front to plug in the a, but then afterwards you can check any x value you want. You know what I'm saying? And then at that x value, you create your point. So like the point 1 would be 1, 2. You have your point, you have your slope of negative 2, then you can create your tangent line. If I was like, oh shoot, I meant 2, well that would be the point 2 comma 1 if you plugged it in. At the point 2, 1, the slope was negative 1/2, and you can create your tangent line. Does that make sense, you guys? You created kind of a little trick to solve for any x value. Alright?